Hello, welcome to Selected Advanced Physics for High School.
We will discuss how did Newton determine the value of G when he discovered the law of universal gravitation. So first see what the law is. What is Newton's law of gravitation? The law says that any two objects in the universe attract each other with the same force. This force is proportional to the product of the masses and inversely proportional to the square of the distance between them. So if you have two masses, m1 and m2, then the force is given by G times m1 m2 by r square. Here G is a universal constant of proportionality. You can think of G as the amount of force between two objects 1 kilogram each and separated by 1 meter. You can just plug in m1 equal to m2 equal to 1 kg and r equal to 1 meter per second square, and you will see that the force is the value of G. Now this value has to be determined experimentally. How could Newton know this value? The amazing thing is that he could estimate this value by cleverly making use of existing information. So to calculate the value of G, to calculate G from the equation F equal to G m1 m2 by r square, you need to know F, you need to know m1, m2 and r. Correct? So you have to choose, you have to select two objects at a known distance. R with known masses also, two objects with known masses. And so that we know the force between them. So what Newton did, he took m1 is, the mass of a stone or a coconut, whatever you can check. Okay, m2 he took as the mass of the earth. In that case, the r is the radius of the earth. Because this is the distance between the stone and the center of the earth. Because earth is a spherical object, so the earth attracts as if the whole mass is at the center. So let's see what happens. So we still don't know what, so r equal to radius of the earth. This information was known for a long time, for 2000 years. Okay, so now we still don't know how to find F. So here Newton realized the force is also equal to m1 times g, where g is approximately 10 meter per second square. Because we know that every object falls to the earth with the same acceleration. So the mass of the particle is m1. Therefore, you can put the force as m1 times g. So now you can combine these two things. So you can write m1 times g equal to capital G m1 mass of the earth divided by Earth's radius of the earth square. And you see, now you see m1 and m1 cancels out. You don't really need to measure the coconut, mass of the coconut or the stone. And you get G equal to capital G times ME by R of E square. So this is the equation that will help us now to calculate the value of G, because this is known. Small g is known. This is known. So we only have to know the mass of the earth. And that's what we're going to do next. So we have got 10 meter per second square equal to capital G, mass of the earth divided by the radius of the earth square. Now, before we plug in the value of the radius of the earth, let's understand how to calculate or how to estimate the mass of the earth. Now, if we assume the earth to be a perfect sphere, then the mass of the earth is the volume of the sphere of radius RE times its density. Of course, the earth has different densities, different place, so we'll take an average density. Now, so this will be the volume of a sphere is 4/3 pi, radius is RE, so 4/3 pi cube times the density. So now what you have to do, you plug it all these things here and you get 10 equal to G 4/3 times pi R cube times density divided by RE square. So again, you see these two things partially cancel and you get only R of E here. So you get 10 equal to 4G/3 pi RE times density. So now you have to estimate density of Earth. So there is no easy way of estimating this, but you can see that the Earth is a lot of it is water, and then there are rocks, sand, and everything. So density of water is approximately 1000 kg per meter cube. So 1 cubic meter of water weighs 1000 kg. And density of rocks, some heavier rocks, is approximately 8000 kg per meter cube. So you take an average between the two. You don't know any better, so you take a guess here. So let's say this average density is something like 5 times 10 to the power 3 kg per meter cube. Okay, so now we have got everything except that you have to know the value of the radius of the earth. So the radius of the Earth is approximately, if you think of it as a perfect sphere, it's like 6,371 kilometers. So you can take it as just as 6,400. So you can write it in terms of meters now, because everything we have to convert to meters in seconds. So this is meter. So now we have got 10 equal to 4 pi by 3 times 6.4 times 10 to the power 3 times 5 times 10 to the power 3, okay, and times g. So please remember that here I got meter in units of meter, and this is kilogram per meter cube. And of course, on the right hand side, this 10 is actually 10 meters per second square. So we plug this all in now, and let's see what we get. So I have erased some stuff here to make space. So you can get now G equal to, just solving for G, is you get 3 by 4 pi 1 over 10. That 1 over 10 comes from here, divided by 6.4 times 10 to the power 3 times 5 times 10 to the power 3. And what will be the unit of this object? So this will be Newton. So this will be Newton units. Newton meter square by kg square. We should check this carefully, but I think this will be the units. Actually, it's exactly the other way around. So let me erase that. It's Newton. No, it's correct. I'm sorry. Newton meter square per kg square. Okay, this is the correct one, I think now. All right. Oh, I think I made one more mistake. This is not 1/10. This is not 1/10. This is actually multiplied by 10. This is actually 10 times. So let's check this now. So plugging all these values in, what I get is G equal to 7.7 times 10 to the power minus 11. And again, the unit, let's make sure you get the unit right. It's Newton meter square per kg square. Newton meter square by kg square. Actually, the value is 6.6 times 10 to the minus 11. So we're quite close. Okay, so that's all. We have calculated, or actually estimated, the value of G like Newton might have done. That's a great satisfaction. So with this, we'll close this edition, and I just want to say thank you.